Hey, it's Brian. So we have one more topic to talk about this week, and that's torque. And here's the crux of the biscuit. Forces make things move. Torques make things rotate. So if you're pushing on your bike pedals and you want to make your bike wheels go around, the pedals are rotating, the tires are rotating. Those are questions of torque. And actually, if you're swinging a club like this polo mallet here, that's a rotation question as well. That's the type of thing we're going to be looking at in this section. And this is in Chapter 7. And there's two sections in Chapter 7 we're going to look at, 7.3 and 7.4. 7.3 deals with torque. 7.4 deals with a specific kind of torque called gravitational torque. Now here's the thing, up until this point, when we've been drawing pictures of objects, I would say like, oh, okay, here's a bush baby, or here's a runner, or here's an aircraft carrier. It didn't matter. We just draw everything as point objects. We use the so-called particle model. But at this point, it's time to get real. Okay, we use the particle model, but the particle model is not working for us anymore. We have to get real. You are not a point mass. You're not a point mass. You have spatial extent. And there's a couple of consequences of this. And the first and the most important thing for what we're going to deal with today is this. And the main consequence we're going to be interested in today for the fact that objects have spatial extent is this. Okay, where you push on something makes a difference. Okay, and also the angle you push at makes a difference. So if you're trying to get a merry-go-round going, you want to push on the outside edge, and you want to push in a direction that is perpendicular to the radius. Okay, so if I draw a line from the center to where she is pushing at a perpendicular angle. She is pushing at an angle that is optimized to provide the most torque. Well done, young person. Now, let's talk about torque. Now let's look at a definition of torque. So whenever you're working with torque, you're working with an object that has some spatial extent. So I'm looking at this wrench here, and this wrench is turning a nut, and the whole system is going to pivot about that point right here. Forces are applied at this point right here, and we said where the force is applied matters. Now the distance from the pivot point, so where the force is applied, we're going to call the distance r. Okay, and also the angle that you apply a force at makes a difference. So if I apply a force like this is kind of a general force vector. It turns out the component that is parallel to r, that's not helpful. You know this. If you pull in that direction, you're just going to pull the wrench off. That's not going to rotate the wrench. That's not helpful. You want the component that is perpendicular to the distance from the pivot point to where the force is applied. I want the perpendicular component of the force. So our first definition of torque is this. The torque is equal to the distance from the pivot point to where the force is applied times the perpendicular component of the force. Now it turns out you're generally applying a force in order to create a torque in the problems we'll look at. And so the forces are already perpendicular. In that case, we can just take the force F as long as it's perpendicular, and we can just take that component and it's just F times R. Now I want to talk about units. This is a product of a distance times a force. And so the units of torque are newtons times meters, Newton meters, okay? Now there's a second way that we can compute, because sometimes it's a little bit complicated to figure out what the angles are, etc., etc., etc. And so I can also do this. I'm going to take the force that's applied. And so let's look at the force vector that's applied right here. The force is applied like so. Okay? And then I'm going to take the line of action of the force. So imagine like tracing out a line that is along the line of the force like so. And then I'm going to define a perpendicular distance to the pivot point. So I want this distance right here. And I call that distance r perpendicular. That is known as the moment arm. So I can take the torque is equal to the force times the perpendicular distance, i.e. the moment arm. And we'll see a case or two where that applies. As a matter of fact, that's the most common thing which we're going to be looking at in biological systems. Now let's look at a couple of examples of torque problems. I've got a pulley here. Okay, I've got a pulley here, and the question asks which way will it rotate? Well, since it talks about rotation, this is clearly a torque problem, because remember, forces make things move, torques make things rotate. Now, there's a torque on this pulley produced by tension in two ropes, and one rope is suspending a 2.5 kilogram mass. The other rope is suspending a 4.0 kilogram mass. So the question is, which one of those torques is bigger? Let's just work it out. Now, if I have a 2.5 kilogram mass suspended from a rope and it's stationary, the tension in the rope is going to be equal to the weight of the 2.5 kilogram mass. And to a good approximation, that's 25 newtons, okay? There's a tension in the rope over here as well. It's a 4 kilogram mass, and so the tension in the rope is going to be 40 newtons. I'm just doing a quick estimation. I'm assuming G is equal to 10 here, and actually that wouldn't affect the outcome. So I have a bigger force on the right than I do on the left. But let's look at the distance. And the distance from the pivot point, and the pivot point for this pulley is pretty clearly marked. It's right there in the center. That's my pivot. The distance from the pivot to where the force is applied is 0.2 meters on the left and 0.1 meters on the right. So remember how we compute torque. Okay, torque is equal to R times F perpendicular. Now notice this. Both of these forces are applied perpendicular to those distances. So we don't have to worry about F perpendicular, it's just F. So we can get rid of that symbol. So it's just equal to R times F. R on the left is 0.2 meters. F is 25 newtons. And so I end up with a torque of 5 Newton meters. That's the torque due to the 2.5 kilogram mass. Now on the right side, I can compute the torque, R times F. Well, the radius, or the distance from the pivot points where the force is applied, is 0.1 meters. The force is 40 newtons. And so I end up with a torque of 4 Newton meters. So check this out. The heavier mass, the 40 Newton, makes a 40 Newton tension in the cable, or in the rope. The lighter mass makes a 25 Newton tension in the rope. But the fact that they're applied at different distances, and the 25 Newton force is applied at a greater distance from the pivot point than the 40 Newton force, makes the 25 Newton force basically punch above its weight class. It is able to produce more torque, even though it's a smaller force, because it's got a bigger value of R. And so the torque is bigger on the left side than on the right side. And so as a consequence, this whole pulley system will rotate counterclockwise. Okay, that's the way torques work. Now, let's do some more torque calculations. And this is a classic, okay? It turns out there's standards for like how tight you make jars. And it is supposed to take a torque of about 2 Newton meters to open a jar. And that's kind of a standard. They tighten jars that tight. And if you can apply a torque of 2 Newton meters, you can open the jar. So here's a question. Suppose you grab the jar with your hand and your thumb and fingers exert equal magnitude forces on opposite sides of the lid. The question is, what is the magnitude of each of the forces? So basically we're saying, how much force do you have to apply to opposite sides of the jar lid in order to produce a torque of 2.0 Newton meters? Let's take a look at this one. Okay, first thing we're going to do is we're going to strategize. Okay, we're going to strategize. And I'm going to say, since I'm trying to make the jar lid rotate, this feels distinctly like a torque problem. Okay? Next piece of the puzzle is I'm going to prepare. And my preparation stage is going to be just like my previous ones. I'm going to draw a picture. I do love pictures. And in torque problems, you must draw a picture. It is absolutely mission critical. And the picture I'm going to draw looks like this. Here's a picture of my jar lid, and I'm applying a force at opposite sides. So I draw a picture of the situation, and I draw the forces where they're applied, and they're applied at opposite sides, and of course they're in opposite directions. You know that's how it works. And so I end up with forces that look like that. I'm also going to represent the distances, and I have to choose a pivot point, and a jar lid, of course, rotates around its center. So I'll take my pivot point there. I'm going to take my distances from the pivot point. That's just the radius of the jar lid. That's 0.035 meters on one side, and of course 0.035 meters on the other side. And so I've got the forces, and I have the distances. And I want to note this. The total torque that I'm applying, I expect the total torque to be equal to 2.0 Newton meters. That is what is required to open the jar. Okay, so I'm just going to compute the total torque, and I'm going to set it equal to 2.0 Newton meters. And with that, we are ready to do some solving. Okay, now for solving, I'm just going to compute torques. And the torque due to the first force is equal to the force, or the distance, times the force, r times F. And the distance, of course, is 0.035 meters times my force F. Okay? Now I have a second torque due to the other force that does this. And I want to notice something about these forces. The force on the left points down. The force on the right points up. And so the net force is 0. The jar lid isn't going anywhere, but that's not your goal, is to make the jar lid go somewhere. Your job is to make it rotate. But check this out. The force on the left makes the jar lid rotate counterclockwise. The force on the right also makes it rotate counterclockwise. And so I'm going to sum my two torques. They are both in the same direction as far as the rotation is concerned. Okay? So my total torque is just going to be equal to twice the original torque. The total torque, or the net torque, is going to be equal to 2 times 0.035 meters times my force in newtons, and that's equal to 2.0 Newton meters. So I have 2.0 Newton meters is equal to 2 times 0.035 meters times F. And I have everything I need to calculate F. And if I do that, I get a force of 29 newtons. Okay, and 29 newtons, remember about 5 newtons is a pound, so this is something like 6 pounds of force. And that's not terrible. That's not terrible. That seems reasonable in terms of what I've used to open jars before. So my assessment is that the final answer that I get seems reasonable in terms of how the world works. And that is one example of a torque problem. Now we're mostly going to be interested in situations that are more complicated than this. So a number of years ago, I broke my ankle, and one of the cool things that happened as part of that was they took x-rays of me, and I knew exactly what I was doing, and there's distance scales on the x-rays. And so I said, I can use these to do some physics problems, and let's do one. So here's the question. They would have me, when they were taking x-rays, stand on the toes of one foot. And the goal was to produce a torque about my ankle joint. Now, why they did that, I'll talk about later. But for now, let's just compute what torque would be provided by that force. So let's think about how we solve this. First step, we're going to strategize. And to strategize, we know what to do. We're just going to say, what type of problem is this? This is a torque problem. We know it's a torque problem, so we're good to go. Now for preparation, what we're going to do is this. We're going to draw a picture. And in the picture, I need to clearly locate what is the object that is rotating. Well, the object that's rotating is the foot. Okay, and we also have to know the point about which it rotates. And the point about which my foot was rotating is my ankle, but specifically this point right here. So I have an object that's rotating. I have the point about which it rotates, and then I have to have forces that are being applied to it. Now think about the forces being applied to my foot by things that are external to me. And the only thing that's touching my foot is the ground, and the ground is exerting an upward normal force. And I know the magnitude of that normal force. The magnitude of that normal force is just equal to my weight force, which was 700 newtons at the time. Okay? So I have a force, I have an object that is rotating, I have a pivot point. I am ready to calculate some torques. Now our first definition of torque looked like this. We said torque was equal to R times F perpendicular. But that's a little bit tricky, because what I would have to do is say take the distance from where the force is applied to the pivot point, and then I have to know this angle, and then I have to compute components. But the thing is, I can't compute the angle because I don't know this distance right here. I don't know that distance. So as a consequence, I can't do that. This way of doing it is not going to be helpful. So as a consequence, what we're going to do instead is to say, let's take our second definition, that the torque is equal to R perpendicular times F, and let's do the moment arm. And this is almost always the situation for biological systems. So we'll take the line of action of the force. And remember, we take a line that is kind of like along the force vector, and we take the perpendicular distance from the line of action of the force to the pivot point. And that's clearly labeled in the diagram. That's 12 centimeters. That's 0.12 meters. So we can compute a torque because we know that we're computing the torque this way. Torque is equal to R perpendicular times F. And we know the force that's acting. Okay, the force that's acting is 700 newtons. We know that. We also know R perpendicular, that's 0.12 meters. And so we're ready to solve. And if we do that, we end up with a torque that is 84 Newton meters. Okay, so that's a lot more than the force necessary to open the jar, but typically the forces and torques in your body are kind of like significantly larger. This is the type of problem which we're going to solve going forward. Okay, and I want to do a quick preview of the kind of thing that we're going to see. Now typically if we're considering a situation where something's rotating, like this teeter-totter here, and the teeter-totter clearly rotates around a pivot point, okay, and forces are applied to it which produce torques. These two people sitting on the teeter-totter each exert a downward force on it, okay? And the question is, if we want the people to be having a good game, the torques that they exert, the person on the left making it rotate counterclockwise, the person on the right making it rotate clockwise, the torque should be approximately equal. So as a consequence, they're going to have to sit at different distances because they have different weights, and so the forces that they apply are going to be different. And so as a consequence, the distance that they sit from the pivot point is going to have to be different as well, because we want these two torques to basically balance. We want this teeter-totter to be approximately in static equilibrium. We want it to be not going anywhere. That's the type of thing we're going to be dealing with in Chapter 8. And as a quick warm-up, I want you to think about this. Who needs to sit closer to the pivot? The person with the larger mass or the person with the smaller mass? You know, but can you make sense in terms of the torque picture? Well, if I want the torque of the person on the left to equal the torque of the person on the right, okay, what that means is that R1 times F1 should be equal to R2 times F2. By the way, you'll notice that I've stopped like even doing perpendicular because we're assuming that the forces are acting perpendicular. They typically are. R1 F1 is equal to R2 times F2. If I have a bigger force, I need a smaller distance in order to make things balance. So who sits closer to the pivot? The person with the larger mass. Now, the type of problem we're going to look at in Chapter 8 is going to be situations where we're looking at static equilibrium and we're balancing torques in situations like this. So if I have an upward force due to the floor on my foot, it has to be balanced by another torque. And the torque in this case is the torque due to my Achilles tendon. We have to balance those. We can use those to compute things like what is the tension in the tendon? And that is a problem that we will solve. And we'll also talk about this. Why would they want to take an X-ray with you standing on the toes of your one foot? Like, why would they do that? That hurt. Why would they ask me to do this? There was a reason to it. There was a method to the madness. And that's the sort of thing we'll talk about when we talk about static equilibrium. That is the stuff that is the subject of Chapter 8. Tremendous amount of biological applications, and I am looking forward to it ever so much.